Okay, welcome in. This is our last of three videos in this series on deriving the initial OLS, ordinary least squares, regression coefficients. In our first video, we talked about what regression means, fitting a line to data. Alpha, beta x predicts our y value, we call it y hat. And we talked about how we find the alpha and beta that minimize the sum of the squared errors. So our actual y minus our predicted y, and we square that to get our error. And again, we square it because it keeps it positive and also punishes large errors. We talked about the way to actually solve this. We take a derivative with respect to alpha, with respect to beta. We get two equations, set them equal to 0 because the derivative at the optimum point is going to be 0. And we solved our alpha equation, and we got alpha in terms of y, x, our data y and x, and beta, which is great. However, we need to get alpha and beta in terms of solely x and y. So that's what we're going to do now. We're going to finish our derivation. We're going to do a lot of math, just a lot of algebra and a lot of some SUM algebra. One really useful fact that we're going to need is that x bar equals the sum of x times n. And this is intuitive. Remember, when I'm doing sum, I'm doing from I equals 1 to n. If I just did, I'm sorry, that is not correct. N x bar equals the sum of x. Because the sum of x divided by n is x bar, or the mean of x, so n times x bar is the sum of x. That's a term we're going to use a lot in this derivation. Okay, so let's start doing our math over here. We have to erase some stuff. We can start out, and we're going to start by expanding our derivative with respect to beta. So I have this xi term. I'm just going to apply this xi to each of these. I remember I have this negative 2 term. I can just divide each side by negative 2 because 0 divided by negative 2 is 0. So I get 0 equals the sum of xy, xi, and this, I'm going to do the parentheses because it's just, I want to sum with respect to that. Can you see that okay? Yeah, that's visible. Minus alpha, sum of x. Remember, I can take the alpha out of the sum because it doesn't vary with I, minus beta. There should be a, oh, you know what, I'm sorry. Well, I just realized that I forgot to write the xi here, which didn't impact the solution in my last video because I wrote the xi here, so we're all good, but the xi should be here. Probably screaming at me in the last video. But anyways, we got our beta times the sum of xi squared. Awesome. Your IQ drops like 15 points when you're doing that in front of other people. Okay, so that is our first step. What we want to do now, well, we've solved alpha in terms of beta over here, so we're going to want to plug that in. So let's do equals sum of xy, I, minus y bar sum of xi. I can put y bar outside of the sum because y bar is just a number. It could be like 3.2, it's just the average of y, plus beta x bar sum of xi. And again, here all I'm doing is I'm plugging alpha, like y bar minus beta times x bar equals alpha. I'm plugging that in to here. And then that, that's why I get basically the sum of xi times, there's my y bar, and there's my beta x bar over here times the sum of xi. Minus, let me erase this, minus beta sum of xi squared. Okay, need another parenthesis. Ooh, a little sloppy, but you kind of get the gist. Okay, so that is step 1. Now, what we can do is use our very useful fact that the sum of xi equals nx bar, and plug in. So again, first term unchanged, as it will always be. Nx bar for this term, so minus n x bar y bar plus n x bar for this term, so n beta x bar squared. Just want to make sure that's good. Minus beta sum of xi squared. Awesome. So it's still ugly, but we're starting to get there. And actually, this whole thing equals 0. I put 0 up here. And actually, we're kind of getting close. We have two terms with beta. We have two terms without beta. So what we can do is we can move these two terms, I'm going to go on this side so you can see, we can move these two terms to the other side of the equation. We can factor out beta from these terms and divide this side by these terms. So I'm just going to write that and then we'll talk about what I did. Beta equals, sum of xi, yi, is n x bar, y bar, parentheses, over sum of x minus, just make sure I did that right. Yeah, awesome. So all I did was I moved the beta terms, I added this term to the other side, subtracted this term, then I divided, you can see this term is here, this term is here, so I divided these terms by the sum of xi squared, which is from this term, and the n x bar squared, which is from that term. And I have my result with respect to beta. So, that's awesome. Technically, we're done, right? We have our beta in terms of the x and the y, and I'm going to pause here to just talk about the significance of this. Now this is saying, given whatever data we have, we can very easily calculate. You can do it by hand, of course, but you can do this easily in R or any sort of programming language. We can calculate our optimal slope, optimal in the sense of minimizing the sum of squared errors, and then given our optimal slope, we can plug it in and calculate our optimal intercept. That'll give us our line of best fit. So very cool, very cool result. We now, we figured out what our best line of best fit is, and we figured out how to calculate it given the data. We're gonna do a little bit more work, just like tedious algebra, because it's correct, but it's not the general form that you see beta in, so we're gonna do that so you are familiar with what the general form looks like. And I'm just looking at, you can see the algebra, so that's good. I'm writing small because we have a lot of algebra to do, sadly. Okay, so let's start with the denominator. With the denominator, we're going to do a little trick, and again, this is just reworking it to look like the more familiar result. We're going to do a little trick, and we're going to add n x bar squared and subtract n x bar squared. So we get sum of xi squared, am I going to be able to fit this, minus 2n x bar squared plus n x bar squared. Okay, and again, we're just subtracting n x bar squared, that's why we have 2n x bar squared plus n x bar squared. And this is supposed to be in one line, I didn't have space. And what's really neat about that is that, first of all, we are starting to see something that looks like a quadratic expansion. And what we can do is we can reverse engineer our nice result over here. We have n x bar squared in this term. We can imagine that as n x bar times x bar, and the first n x bar is going to be equal to, just the sum of xi times x bar. Wait, make sure that's right. Yeah, okay, awesome. Times x bar, and then plus our n x bar squared. Okay, so what did I do? 2n times x bar, the first n x bar becomes the sum of xi, right? And sorry, there's a 2 here, minus 2. Sum of xi, and then I have another x bar left over. Okay, so it looks like I'm doing something weird, but I'm just plugging in 2n x bar times x bar, the first n x bar becomes sum of xi. Now I have a squared quadratic, or a quadratic, or whatever you want to call it. Now I have sum of xi minus x, sorry. Okay, first what we have to do is these sums, this sum only applies to the xi squared, this sum only applies to this xi. Let's rewrite this pulling the sum out front, and this is just annoying stuff. So again, we're summing from I equals 1 to n. We have the xi squared, we have the 2xi x bar. The x bar just comes along for the ride because it's a constant. What is interesting is that this term, we can rewrite this as plus x bar squared. Where did the n go? Well, now we're summing this whole term. Before we weren't summing this term, it was just sitting there. Now we're just writing this as the summation of one big term. X bar squared is a constant, so if we applied the sum here, we'd get nx bar squared, which is what we got here. So we're just rewriting it to collect everything under one sum, is the idea. And now that everything's under one sum, now we can just say, okay, this is xi squared minus x bar squared. sorry, xi minus x bar squared. Nice. Computer's gonna die. Awesome. And you can see how that, now everything is under one sum, and this is just, like x minus y squared. Awesome. So that is our denominator. And this is, you can see this is a nice, it's like cleaner to look at than the actual denominator we got. Each x value minus its mean squared, I think, is like a little bit nicer than just, this ugly thing. So that's good for the denominator. And now let's do the numerator. The numerator is a little bit weirder. We're going to start at the answer and work backwards and show that it's right. So we're going to start with the sum of xi minus x bar times yi minus y bar. So I'm telling you that this is the answer, and I'm going to prove it to you by expanding this out. So first we expand out. This is going to be this sum is applying to all the terms. So the sum of xi yi. Do I want to expand the sum out? No, let's do this first. Sum of xi yi minus xi y bar minus x bar yi plus x bar y bar. So I'm just, multiplying, sorry, just keep getting off camera, multiplying each of these terms. My x's and y's aren't very clean, so let me do that, clean it up. And the sum applies to all the terms. And now I want to distribute the sum, kind of like before we undistributed the sum, we pulled it out. Now I'm going to distribute it for each of the terms. So sum of xi yi term minus y bar. Remember, y bar is a number, it's a scalar, it comes out of the sum. Sum of xi minus x bar, scalar, comes out of the sum, yi. And then again, x bar, y bar is a number, it doesn't vary with I, so that's just plus n x bar, y bar. Okay, and now we're close to done. We're going to use that trick up there, all the way up there, that the sum of xi is equal to n x bar. Okay, and we're going to use same thing for yi. The sum of yi is equal to n y bar. So we can write this sum of xi yi minus n x bar y bar minus n x bar y bar plus n x bar y bar. These last two terms cancel, and we get this term, which is what we have in our numerator up here. So basically what I did was I said, this is the result, and we expanded it. We kind of did the opposite thing we did with the denominator. We expanded it, and we showed that it was equal to the denominator. So, all together, when you see beta, you're going to see, the result you're more likely to see is the sum of xi minus x bar times yi minus y bar all over the sum of xi minus x bar squared. Okay. And again, this is a little bit cleaner than what we did before. The denominator, we already talked about. The numerator, it's each x minus x's mean times each y minus y's mean. A little bit cleaner to look at than like this weird thing. And again, the sum is applying to all terms. So we did it. I talked about earlier how, this is just a cleaner reworking of this, but, it's useful to see where this comes from because this is how it's always written in all the text and everything. And again, just to, repeat, we now, for any data set or any x and y, we can calculate automatically, figure out the optimal alpha and beta that, that fit this line of best fit in the best way. Here's how we calculate the beta. And then we go and we take the beta and we plug it in to get the alpha. And again, we're just this is from the data x and y. We have our data. We can do it by hand. We can do it by computer. Whatever. So hopefully this makes sense. A lot of algebra in this video, but hopefully this peels back the layers of regression. I think it's very good to understand how it works from front to back, and hopefully you agree that it's actually not so bad once you get working. Maybe some of the sum math, like summing from I to n, dealing with the scalars and adding things, it is annoying, but it's good to get more familiar with, and hopefully it wasn't too confusing. But we'll do some more videos on more advanced regression techniques, machine learning techniques, but hopefully you enjoyed this one. We'll see you next time.